Hey folks, welcome back. So today we are going to see this problem 863, which is all nodes distance k in a binary tree. The problem statement is basically, let's say you have a tree like so, A, B, C, D, E, F, G, right? This is the given tree. I'll call it as root. Okay, this is the root, and there is a target is equal to C, and K is equal to 2, right? So the question is, if you start at C, what are all the nodes that are K distance 2 steps away from C? So let's use a red pen. So the distance between C and F and G is 1. Between C and A is 1. So if you traverse this way, C to A is 1, A to B is another 1, so total 2. So the answer is, in a list you will just provide B. Okay, let's see a different target, right? If the target is equal to B, K is equal to 1, what will be the answer, right? I'll use black pen. Okay, now this is B, this is distance 1, this is distance 1, this is distance 1. So the answer would be here D, E and A. Now ideally for the distance problems, you would generally go for a BFS solution, right? Because BFS is famous for minimum distance calculation and all these distance calculations. But the problem here is you are supposed to go from the target node back to the parent as well. But tree is unidirectional, meaning the direction is set from top to bottom, right? But how would you go back? So if you think about it, this is not a tree problem, this is basically a graph problem. If I can convert this tree into a graph, something like so, A, B, C, F, G and D, E, right? I deliberately try to move out of this tree structure. Now if you think that this is a non-directional graph or a bidirectional graph, so like that, then you can start at B and you can traverse in any direction and calculate the nodes which are at distance k, right? Using this same idea, the first step is to basically prepare a graph. Step 2 is do a BFS, and basically that's it, right? So how would you prepare a graph? So graph, you can basically say something like, if you start at the root, it's basic DFS, very simple DFS graph conversion. You can solve it by DFS. You can create a map. You can create a map of the tree node, which is the denotion in LeetCode, and its neighbors will be list of other tree nodes, right? And you can call it graph G. In graph G, the way you can prepare is key and value. So based on our graph, what we can do is A has no parent but has two children, B comma C. B has two children, D comma E, but also has an A, right? And C has similarly A, F and G, and D doesn't have children but has a parent. E has a parent. And for space constraint, I'm just gonna write it right here. This is E, right? Okay, F and the G, they don't have children either, so the parent will be C, and this is the key and the value, right? So you can create a graph like this, right? So your step 1 is done. Then it's basic BFS, right? Basic BFS, this is step number 2. Step number 2 BFS is very simple. You take a queue and you add a tree node in it, right? But which tree node would you start? Because you have converted this into a graph and you're trying to locate from the target, from this target position to 111 distance, right? Your first addition to queue will be queue dot add. Our target is B, this is target, right? And you can just do a simple while loop over the queue not being empty, and standard, right? You just get a size, then you for loop over size, and in the for loop what you're saying is you're getting a current node which is queue dot poll. Okay, now remember we have converted this from a tree to a graph, meaning the deliberately we have converted an unidirectional graph into a bidirectional graph or a non-directional graph, meaning I can go from one node to all its neighbors. Because I have that flexibility, I definitely would like to add a visited concept, visited node concept. This could be simply like a set of tree nodes. Okay, the moment I'm polling, the moment I'm getting the node out of the queue, all I'm just going to do is I'm going to add it into this visited set, visited dot add, and I'm going to add this current node, and now I need to check what my neighbors are. So I'll get list of tree node as neighbors is equal to graph, the one we have prepared right here. Oh, I call it as G, right? Okay, let's do G. G dot get of current. Now I have a list of neighbors. So inside this neighbors, for tree node n of neighbors, as long as if they are not in visited dot contains n, you are good to add in the queue. You are good to add in the queue, which is n, right? So pretty simple. Now the next question is, where are we calculating the k? Where are we calculating this case the distance, right? And because we are going level by level, meaning from the bit node, I'll use a different pen, let's say blue. From this node, the moment I traverse this way, and this way, that is one level. From that level, so instead of this k being 1, let's say if it is 2, then I would have to, from here I cannot go further, so I would have to go further from this side, and eventually my answer would be C. So you have to increment or decrement the k after this for loop, which basically ends here, k minus. And now that you have incremented, where are you adding to your result? Basically you would have a list of you'll have basically a list which is basically the result, correct? So you would just put, you can just put if condition right here, if k equals 0, then very simply you are just going to say result dot add current. That's it. You can optimize this a little bit, saying that, hey, if k is less than 0, do I still have to do all this? No. So you can do all those optimizations, but that's the general idea. The problem is a medium level problem. The key is to convert the tree, a unidirectional tree, into a bidirectional graph, and from there it's actually pretty simple. So I hope this makes sense. Okay, and the code for this is in the GitHub. The link is in the description. Okay.